Today we're talking about exponential growth and decay. So exponential growth occurs when a quantity increases by the same factor over equal intervals. So remember, with factors, we're multiplying something over and over again. So the exponential growth functions. So here is the function and what it looks like. We have this y equals a times 1 plus r raised to the t power, where a has to be greater than 0 and r is greater than 0. So let's just talk about what all these pieces mean. So the 1 plus r on the inside is really talking about our growth factor. Okay, so growth factor is the 1 plus the r. Okay, it's how much we are multiplying each time we go forward. The 1, these are both in decimal form, so the 1, if you think about it, represents the 100%, or our starting point, and then we are adding on some percent. So the r represents our rate, which is as a decimal. So it is the amount that we are growing by. Okay. Y is basically our final amount. Okay, it's how much we have after that growth has happened. Okay, that's our output after all of that. A represents our initial amount, which, remember, we think that's also our y-intercept. Back when we did the exponential functions, y equals a b to the x, remember that a was our y-intercept, and t stands for time. How long is this growth happening? Example 1. The inaugural attendance of an annual music festival is 150,000. So that's our initial amount. The attendance, y, the final amount, increases, so that's an important thing to notice. We are increasing, so getting larger or growing, by 8% per year. So remember, we're going to use the decimal version of 8%. We're not using 8. Okay? So write the exponential growth function that represents the attendance after t years. So basically, I'm plugging it in. So we don't know the growth at that point. The A, or the initial amount, is 150,000. We always have the 1, because we're keeping that 150,000, and we're adding 0.08 each time. Then we are raising it to the t. And then we can simplify this to make it a little bit better. 150,000, 1.08 to the t. And then something to think about is when I see one of these functions that has this growth factor greater than 1, it would definitely be growing because we're bigger than the 1 or the 100%. All right, so now, second question is, how many people will attend in the 5th year? So 5th year, that's now our t, and we're rounding to the nearest 1,000. So you always want to be looking for any kind of rounding. So basically, we're just going to plug in the 1.08 raised now to the 5th power, remembering when we talk about using exponents in GEMDAS, exponents would come before the multiplication. Don't fall into the trap of saying 150,000 times 1.08, then raise it. We do the raising first. Definitely a calculator here. And if I do it out, it comes out to something about that. The nearest 1,000 would mean that we would round it. The 399,000 wouldn't make it go up. So in year 5, we would expect 220,000 people to attend. So exponential decay is when a quantity is decreasing. Oh, not that. By a same factor over interval of time. So it's the opposite of the growth. The only difference in the formula is that our growth factor is now called the decay factor, right? And the major difference is right here. So notice that we're subtracting our decay rate. Okay, so R is our decay rate, still as a decimal, and this whole piece is a decay factor, so the 1 minus R. All the other parts are the same. A is still our initial amount, Y is our final amount, and T is still standing for time. But basically, this is when our numbers are decreasing by that same factor over and over and over again. So now we're trying to identify growth or decay. Determine whether these tables are exponential growth, exponential decay, or neither. All right. So what I want to do is I want to look at these numbers. Right. What is happening? So when I look at the y side, I see we are multiplying by 1/3. We always think about our exponentials as multiplying, not dividing. It is dividing by 3, but think of it as times 1/3. Is that the same as I go down? It is the same as I go down. At the same time, I am seeing a steady, constant change of +1s over here. So it's definitely exponential. And because it is exponential, we know that it's not linear, so it's not neither. And because it is dropping, we would say that it's exponential decay. Okay? And the other thing to be kind of watching, we are multiplying by a number less than 1. If you think about it, if I multiply by something less than 1, it is going to continually drop it. And why we're not saying divide, that is kind of how we see the division. So on the second one, so here we are seeing times 2, times 2, times 2. And at the same time, we see a constant change up at the top for my x values of +1s. So again, I know it's exponential. And again, because that number we're multiplying is greater than 1, it is a growth function. My numbers are going up, and they're multiplying by something greater than 1. So now let's look at deciding whether these functions are exponential or a growth or decay, and identify the rate of change. Okay? So looking at the first one, so we see that we have something. If I was to break this apart, it would be 1 plus 0.07 to the t. Okay? So that tells me if I was to do 1 minus r, remember we talked about how this r is the 0.07. If I was to solve this, 1 plus, I can subtract 1 from both sides to get my r as 0.07. So first, because the 1 plus r is 1.07, it's greater than 1, I know it's a growth function, and then the 0.07 tells me that it's a 7%, because we always write it as a percent. It's a 7% growth. Okay, so basically, because this number right here is greater than 1, it's growth. And then when I subtract r from this, it tells me that we grew by 7%. Okay, on the next one, so because I see this factor is less than 1, which tells me that I'm now going to see a decay. And the decay, we have to figure out how much of a decay. So remember, the factor on the inside of my parentheses is 1 minus r if it's a decay. If I was to solve for the r, I get r equals 0.02. And remember, rate is my r as a percent. So it's a 2% decay. Okay, so again, what you're looking for is this number right here. If it's greater than 1, it's going to be a growth. And then you have to figure out how much greater than the 1 is it. That tells you how much it's growing from the 1, which is 100%. If it's a less than 1, it's definitely decaying because it's dropping, and it's going to be how much from the 1 is it dropped each time, and then you turn those both into percentages. So then we want to write the functions and determine whether they're exponential growth or not. So looking at this first one, they have this weird t over 4 thing. So remember, we want to look back and think about our properties. So I'm going to write this first piece here. And I'm going to say, let's put this as an opposite of the power of a power rule. Remember, power means to multiply them. So what I'm doing with that is I am going to put the 1/4 on the inside to keep the t on the outside. Okay, so the reason I'm doing that is that then I can focus on that 1/4. So remember, 1/4 means we want the 4th root of that 0.96. Okay, so if I use the calculator and I run it through, this is going to become 0.99 raised to the t. Now, because it's less than 1, we know that this is a decay. And it doesn't ask this, but we know it's decaying by 1%. This next one's a little bit trickier, so stay with me on this one. So I see this t minus 3 on the outside. Well, when we did our quotient rule, remember you could subtract your exponents with the same base. So does this make sense, hopefully? That if I went backwards and I did this, I would turn this into 1.1 to the t minus 3. So does that make sense? So it's kind of thinking backwards with our quotient rule. So if I think out this a little bit further, this is now 1 over 1.1 to the 3rd times 1.1 to the t. Well, with a calculator, 1 over 1.1 to the 3rd becomes approximately, it's not exactly this, 0.75 times 1.1 to the t. Now, because this number in here is greater than 1, this is definitely a growth function. And again, we're not asked on this one, but this is a growth function of 10% because 0.1 When I move the decimal over is 10%. So compound interest. So you've probably learned about simple interest in the past. It's a much different formula than this one. This is a more realistic form for bankings and for interest rates and for things when people are banks, credit cards, anytime interest is being used. It's a very complicated looking formula, but as you're kind of working through it, hopefully we can make some sense out of it. So the balance, this is your Y, this is how much money you would have after all the interest. P, the principal, is the initial amount of money that you are building interest off of. So because we're building, it will be a growth function, so it's 1 plus, right? So there's always going to be this 100% of what you have already, and then you're adding on based on the interest rate. So the annual interest rate as a decimal is this R value. These N's are talked about as the number of times a year it's compounded. So it's how many times basically it's being calculated. So if it's being calculated yearly, it's just ones, so they don't affect anything. If it was semi-annually, it would be 2 times a year. If it was quarterly, it would be 4 times a year, and then those numbers would get plugged in for those times. T stands for time in years. Okay, so we'll talk about what those look like next. So we are looking at a deposit of 100 in a savings account that is earning 6% interest compounded monthly. So here are some of the things we want to really be noticing. 6% annual interest compounded monthly, right? And we're starting with 100. We want to write a function that represents the balance after T years. Okay, so if I use that compound interest formula, 100 is our initial amount. It's 1. It's always 1 because we're going to keep 100% of that 100, and then we're going to add on. So R, that is your interest rate per year, so 0.06. Now the N, if I think monthly over a year, there are 12 times that we're going to compound this interest, so the N is there. It is also up here. Okay, so we're not just compounding in one place, it's in 2 places. Because remember, T is years, and we need to change that to months. So then we want to just fine-tune this function as much as possible. And if I use the calculator, and I do 0.06 divided by 12 plus 1, I would get this for my growth factor, and I would still have this number out here. Okay, so if somebody said, well, how much am I going to make over a certain number of years, then we could then plug in the T and go from there. So now we're asked to work on a money market account, which is another way to save money. Write a function that's representing the balance after T years. So first, looking at this table, my y-intercept, that is your principal, or your P. So if I just start filling in as we go, we have 100. We know that we're going to be going up as it goes. And then we have to figure out how much is it going up. Well, if I look at my numbers here, remember when you did this last year, change, percent change, okay? So I'm just going to take the first couple numbers. If I take 110, subtract the previous year, I get 10. To find percent change, remember you divide it by the original, that 100. And that would tell you it changed by 10%. Then I move on to the second one. If I do the 121 minus 110, I get 11. And again, dividing it by the original, or the earlier one, I also get 10%. If I do 133.1 minus 121, I get 12.1 over the original, which is still 10%. So basically our R is 10%, which in the function is a decimal of 0.1. And then we raise it to the t. Because we are doing this year to year, we don't need to put the ends because it's just happening year to year. So that would be our function. And to make it a little bit tighter here, 100 times 1.1 raised to the t. Okay, so we're going to graph the functions from a, which was from example 5, and also this function on the graph below. So we got to backtrack a little bit to get the table from the previous one, and then we'll kind of look at what that's going to kind of do for us and compare the two balances. So if I first just set up my graph, we're only going to see quadrant 1, right? The dollar amount, or our balance, would be our y values, and our t would be the time down here, right? I'm just going to go by ones down here. And then I'm going to go up by 25s here. To get to 250. So plotting this first one, just plotting my points, I start at 0, 100. Then I go 1, 110, which is going to be somewhere around there. Then I'm doing 2, 121, which is still right about there. 3, 133, right about there. 4, 146. And 5, 161. Okay, and then I can draw my curve, something like that. So this would be the function y equals 100, 1.1 to the t. Now, we need to go back up here and kind of make a table, because we don't really have a table yet to be able to graph this. So if I was to make a table, t would be my x's, and the y are really my balances coming out. Okay, so I'm just going to do the same table. We're going to do 0, 1, 2, 3, 4, and 5. That's not an 8. And then I'm just going to run through with a calculator. So at 0, the t, which is the 12 times 0 is 0, which makes that 100 times 1 is 100. When I plug in the 1, 12 times 1 is 12, so I'm going to raise that 1.005 to the 12th and then multiply by 100. So I get 106.17. When I plug in a 2, it's now 1.005 to the 24th, then times 100. I'm going to get 112.72. Then I'm just going to keep going, and if you have any questions on how I'm getting these numbers, please ask, but definitely these are numbers that you would let the calculator work it out for you. So now we have our table. So once I have the table, I can come back to my graph and plot these points. Okay, so 0, 100, we're starting at the same number. Then 106, which is a little bit below, but not by much. Then the 112, still a little bit below. 119, still a little bit below. 127, still now getting further away. And then the 134, and when I draw this curve, you can see that we are clearly on a lower path for the first function. So we're clearly earning less money on this first function, which was example 5, versus this new function. All right, so next we want to look at this example. We have the value of a car. It loses 12% each year. This is another word that we will see when we see that, depreciates, which means it's going down. So either of those words is telling us it's a decay function. Okay, appreciation would be growth. Okay, so when I write this function out, y is what we are going to have as a value after t years. The initial value is 21,500. If I am losing 12%, I would do 1 minus 0.12. And again, just to fine tune the function, this is going to give me 0.88 to the t. Okay, so what is the monthly percent of decrease? Well, if you think about it, if it is depreciating 12% over the year, doesn't that mean approximately, right? If it's 12% over the year, it is depreciating 1% per month, right? 12 months, 12% over the year. There you go. So now we want to graph the function, right? And you're definitely using a calculator. And then we also want to estimate what is it going to be after 6 years. So let's make our table. T, and then the value, which is really your y, right? At 0, we know it's 21,500. Again, when I plug in a 1 and use the calculator and run through my function, I get 18,920. For 2 years, it's now 16,649, 60. At 3 years, it is 14,651 and 65 cents. And then we'll go to 4 years to say 12,893.45. Okay, so when I'm graphing, again, we wouldn't really use the negative quadrants here. I would just have positive quadrant 1. This would be our amount that it's worth value-wise. This would be a year that we're talking about. So we'll just spread this out a little bit. 1, 2, 3, 4. Spread it out a little bit. If I go up by 2,500s, yep. We go up by 2,500s. I would just plot my points and then come back and let's look at the graph. So there would be what your graph would look like roughly, again with a smooth curve showing it. Then the question says, what is the estimation after about 6 years? Well, 6 years, if you kind of look at it, is right about here, right? And if I kind of just do an estimate and I'm kind of projecting where is this going to come in, it's going to be someplace in the region of somewhere around 10,000, I would say. So I think a decent estimate is approximately $10,000. So that's using the graph. If I then went to my equation and I plugged in a 6 to our function, it actually comes out to 9,984.68, which is obviously, again, close. So we're going to use that as our estimation to get about $10,000. So exponential growth and decay are really just an extension off of our exponential functions from y equals ab to the x. Please make sure you understand all these little parts, because that's probably the trickiest part, and also practice using your calculators so you can see how they work with exponents and making sure that you can get the correct answers. Thinking about rounding to dollars, which would be the hundredths place. And if you have any kind of questions, ask me when next time I see you.